We now move to our next invited talk, which is on energy efficient modular exponential techniques for public key cryptography. And our speaker for today is Dr. Satyanarayana Vollala. I would like to call Dr. Sanjay Adewal to felicitate Sir. Sir, please. Dr. Satyanarayana Vollala is currently serving as Associate Professor and Head of the Department of Computer Science and Engineering. He has received his PhD from the NIT Tiruchirappalli with his research focusing on the hardware security. During his doctoral degree, he was awarded the prestigious President Fellowship under the TEQIP program. Dr. Vollala has received Best Paper Awards at IIIT International Conferences and holds multiple patents in the area of hardware security and post-quantum cryptography. He has authored and co-authored over 40 papers in reputed peer-reviewed journals and international conferences. He has successfully secured Rs 1.5 crore funding from the MHA, Government of India, under the I4C to organize the Cyber Commando training program. Sir, please.
Yeah, good afternoon, one and all. As of now, everyone spoke mainly about security policies and implementation at system level and organization level. So my presentation is slightly different from the earlier presentations. As an accommodation, we are having certain constraints. Certain constraints. Due to that, we are mainly focusing on theoretical work rather than fully of implementation or design of modules and all. Okay, now today my presentation is mainly based on efficient modular exponential techniques, which is one of my research scholars' doctoral thesis work funded by DST of India. The outline of my presentation involves introduction and energy efficient multi-modular exponential technique. If time permits, we'll also look into concurrent cryptography transformations. Okay, so I will be starting with the basic introduction only. So today we are speaking something means yesterday someone has created or given a thought to discuss or do something on that one. So that is why I'm to know the essentiality. Yeah, okay, sir, no issue. To know the essentiality of why we need to focus on modular exponential technique, we should know where exactly we are using those techniques and all. So nowadays, every security, whether it is information security or network security or quantum cryptography or cyber security, the core subject behind that every security is cryptography. We know that is broadly divided into two types. In 1975, Diffie-Hellman put forward the concept of public key cryptography to minimize the secure channel to exchange the information between two parties. Since then, so many cryptographic techniques came into the picture, out of which the widely used cryptographic techniques are, we know Diffie-Hellman key exchange algorithm, RSA public key cryptography, Elgamal public key cryptography, Robin cryptography, elliptic curve cryptography. If you are looking into each cryptography, mainly it is having three operations, like the two cryptographic transformations like encryption and decryption, and one key generation. So if we identify, that means if we look into the three operations, almost all cryptographic techniques, that means public key cryptographic techniques, the fundamental and core operation is modular exponentiation. So that means the efficiency of all the publicly cryptographic systems are entirely depends on competent implementation of modular exponential techniques. As we know, modular exponentiation is the repeated operations of modular multiplication, and modular multiplication is involving trial divisions. So it will come under integer factorization problem. So it is not easy to implement these trial divisions. It is completely different from general division under. So now how we can implement those trial divisions when we are using these cryptographic techniques where ME as a core operation. For that, Montgomery introduced a new concept called Montgomery modular multiplication. In his work, he has converted the entire number system into residue number system where the modulus is exact power of 2. If any modulus is exact power of 2, then the operations, divisions and multiplications are becoming just shift operations only. So performing shift operations are very easy in comparison with multiplication and division. So, and the performance of any system is measured in terms of power consumption, heat dissipation, clock rate, and the number of active cores which are involved in that process. In initial days, most of the people focused on unicore system. So that means the unicore cryptographic system where we can perform only one encryption or decryption at a time. So if you want to increase the speed of that unicore system, we need to increase the frequency of that system, which resulted in high power consumption and more heat dissipation. Sometimes due to more heat, the chip may not perform the exact functioning. That means it may misperform the functioning. Okay, then the multi-core system came into the picture, where a processor is containing 2 or more active cores which are integrated in a single chip but on different dies. Okay, so with the help of this multi-cores, so you can perform a parallel operations, so that it is what is that, saving the time consumption. That means indirectly it is increasing the throughput and reducing the heat dissipation. Yeah, now like for managing the cores, we need a scheduler. If the system is containing 10 cores, then which operation will be given to which core? We need a scheduler. That means in multi-core environment, scheduler is going to play a major role. So when we are designing the scheduler, we need to keep 2 things into mind. One is balancing workload. Another one is the operation must be assigned to a core which is performing the exact what we need the operation. So from this, we can conclude that the major component of every public key cryptography system is modular exponentiation. Then the time taken for evaluating modular exponentiation is depends on the number of modular multiplications involved in that modular exponentiation, as well as time needed to evaluate each modular multiplication operations. So if you are minimizing the number of modular multiplication involved in modular exponentiation, indirectly we are increasing the throughput of the system. So the minimization can be done in many ways. So here we focused on that, skipping the not only improving the performance and of throughput and power, but also the security level of a crypto system. So that means almost all the existing systems like RSA, Elgamal and Robin, if they are using the existing modular exponential techniques, if they are implementing in hardware, that are vulnerable to the side channel attacks. Now so many AI tools are existing to monitor the power fluctuations and time fluctuations. Based on the spikes and power fluctuations, the models may predict the key. So now, to avoid the side channel attack, to provide the more confusion mechanism, we have introduced new techniques. We have introduced that new techniques. One second. Those are called bit forwarding techniques. Now, these are the currently available techniques for evaluating model exponentiation. 4 techniques are available. So almost all technique is vulnerable to the side channel attacks due to the AI tools. Yeah. Now we have introduced certain bit forwarding techniques. Those are bit forwarding 1 bit, bit forwarding 2 bit, bit forwarding 3 bits, and adaptable Montgomery multiplication. That method may not only useful for this bit forwarding technique, you can also use for general evaluation of modular multiplication, which is presenting in any cryptographic technique. So in general, in existing modular techniques, you have to scan the bits, you have to scan the key either from left to right or right to left. So if you are focusing on left to right, for every bit, you need to perform one square operation. And if the bit is high, that means if the bit is 1, immediately you have to perform the multiplication operation. So with that, what is happening? For example, if you are having 3 consecutive ones, all bits are high level, therefore a square operation followed by multiplication operation need to perform 3 times. With that, what is happening? So the power consumption at every bit will be almost equal. By analyzing that graph, yes, intruder can predict that here two kind of operations are happening. Either the bit will be 0 or bit will be 1. That means the number of choices from 2 power 3 become 2 power 2 only. That means you have to predict either it is 0 or 1. Okay, so that means if he is understanding that the power consumption is at high level, then he can predict that the bits are 3 ones, 1 1 1. Like that, he can scan all the bits and he can predict the key. So here in bit forwarding techniques, what is happening is we are checking the consecutive ones. For example, if there are two consecutive ones, we are delaying the multiplication at first bit and performing the multiplication at second bit only. So that what is happening, though there are two ones are presenting, then we need to perform one square operation followed by one multiplication operation. That means two square operations followed by two multiplication operation. But if you are delaying a one multiplication at one bit, then what is happening? In first bit, we are performing only square operation, and at second bit, we are performing one square operation followed by one multiplication operation. That means the power consumption between two bits is becoming different. From that, the intruder is predicting that the bits are 0 and 1, but the actual bits are 1 comma 1 for 2 bits. Similarly, if you are having k bits, if you are having k consecutive ones, so you can delay, that means you can skip all multiplication operations at first k minus 1 once, then you can perform only one multiplication with the help of a multiplying factor at kth bit. Then in the power fluctuation graph, what it is showing, for the first k minus 1 bits, the power consumption level is very low, and at the kth bit level, the power consumption is at high. Then intruder is predicting that the key is k minus 1 zeros followed by 1. But actual key is, we know there are k ones. So in that way, by forwarding the bits and delaying the multiplication, we are not only reducing the modular multiplications, but also providing a confusion mechanism at scanning level. So almost all these techniques are based on the fundamental property of modular arithmetic. So that is nothing but the product between any two numbers with respect to a modular modulus is same as like alpha dot beta mod gamma is same as alpha mod gamma dot beta mod gamma followed by old gamma mod gamma. So now this is the algorithm which we are using, converting our general number system into residue number system, where the modulus n is becoming exact power of 2. So if it is exact power of 2, just we discussed that the multiplication and divisions are becoming shift operations only. Now this is the, like, what is that, a method which we are converting from general number systems into residue number system, and we are calling it as adaptable Montgomery multiplier. So that means we have customized the Montgomery multiplier as per the requirement of bit forwarding techniques. So now this is the hardware architecture of the same algorithm which I have shown just now. So and it will be invoked for every square operation, as well as same thing will be invoked every multiplication operation also. So now this is the existing algorithm where every bit is scanned from left to right, and as I told, for every bit the square operation is must. And if the bit is high level, that means if the bit is 1, then along with the square operation, we also need to multiply. We also need to use multiplication operation. For example, if you are considering the steps 3, 4, 5, 6. So what is happening? So in the third step, I am scanning the bits from k minus 1 to 0. That means from left to right. Then for every bit, I am performing the square operation by invoking AMM for the same values like Ri plus 1 and Ri plus 1. Then I am checking whether the bit is high or not. If the bit is high, then only I am performing the multiplication, otherwise moving to the next bit. So this is the traditional technique which is available. Okay, now our technique, what is happening? So in this algorithm that we are naming it as bit forwarding 1 algorithm, we are forwarding 1 bit. So same, at 5th step, we are scanning the bits from left to right. And at 6th step, yes, I am performing square operation, because for every bit we need to perform square operation. Then I am checking the consecutive occurrence of 2 ones instead of 1 1. If there are 2 consecutive ones, then I am forwarding a bit at 8th step. Okay, again I am performing a square operation, because two bits are there, therefore 2 square operations are required. Then at the 10th step, So a multiplication operation is performed. Here, instead of multiplying the result with M1, I am multiplying a result with M3 so that there won't be any change in the result. Okay, with that, what is happening? For every occurrence of two ones, one multiplication we are reducing, as well as we are also providing one confusion mechanism. At the end, again, the 12th step, again, the whatever the calculations we have done in residue number system will be converted into the natural number system, that means general number system. There we are getting the exact result. Like earlier days, now how we can perform a multiplication and division. So a multiplication can be performed with the help of logarithm. If you are applying a logarithm, then multiplication is becoming addition on the log values. After performing the addition on the log values, if you are applying the anti-logarithm, then you are getting the multiplication of numbers. Same way, we are converting into residue number system. There we are performing the record operations and then converting into the virtual number system. Okay. Now the hardware architecture for the bit for even 1 bit is here. We have also provided this hardware architecture. We are in the phase of design of a chip. Similarly, we can also check the occurrence of 3 consecutive ones. If there is any 3 consecutive ones, same way in how we forwarded 1 bit, we can forward 2 bits at a time, and at third bit we can use the multiplication operation. Now here again, the multiplying factor will be different from technique to technique. In bit forwarding 1 technique, the multiplying factor is becoming M3, that is the power 3, and in bit forwarding 2 techniques, 2 multiplications we are forwarding, hence the multiplying factor is becoming M7. M7, like in bit forwarding 2 techniques, for example, if you are not able to find 3 consecutive ones, the algorithm is also checking the occurrence of 2 consecutive ones. If we found 3 consecutive ones, 2 bit will be forwarded and only 1 multiplication will be performed. And if you are forwarding only 1 bit, that means if you are able to find only 2 consecutive ones, then 1 bit can be forwarded and the multiplication will be done at last bit and that. Okay, so the corresponding hardware architecture for the bit forwarding 2 bit is this one. If you are observing the diagram, there are no critical operations and all except the multiplier. The highest complexity operation is multiplication. All the remaining operations are like only the increment, decrement, addition, subtraction, and using of basic gates like AND, inverter, like that only. So that means though the techniques are involving high complexity operations like exponentiation and multiplication, where it is involving the trial divisions, are entirely converted into a simple operations like subtraction, addition, shift operations, and like applying of logical gates. Okay. Similarly, I'm not going to detail into the bit forwarding 3 algorithm, but we check it up to k bits and all. Like if the key size is 1024 bit, then we have checked up to 64 bits. And for 512 bit, we have checked up to 32 bits. For every like what is that algorithm, like bit forwarding k algorithm, we are able to provide more confusion mechanism as well as increasing the throughput by reducing the multiplications and all. This is the corresponding architecture. Yeah, now when like every time I'm telling that we are reducing the multiplication operation, we have also thoroughly verified not only through implementation of algorithm with the help of a Verilog, we have also designed a mathematical model to compute the number of multiplications required by each technique. So then I'm showing the what is that? This graph is representing the number of bits, number of multiplications required by each technique. So the green spike is indicating the multiplication needed for the existing technique. When it comes to remaining 3 techniques, our proposed techniques. So the last technique is bit forwarding, that means red. One is indicating bit forwarding 3 bit. The blue is indicating bit forwarding 2 bit, and the purple is indicating bit forwarding 1 bit. If you are observing the graphs and all, so you can like come to a conclusion that the proposed algorithms are taking a few number of that means lesser number of multiplications. So in hardware, every operation count, even if you are performing 1 extra shift operation, also extra power and what is the time is needed. When it comes to software, those can be negligible. So we have also computed the clock cycle required by each technique and displayed in this table. And as usual, the proposed algorithms are taking lesser number of clock cycles in comparison with the existing techniques. And you know how we can compute the throughput when it comes to coming to the cryptographic transformations. If the processor frequency is f and the number of clock cycles required for one cryptographic transformation is x, then throughput will be f by x. That means frequency by number of clock cycles. So that means throughput can be improved on two ways: by increasing the frequency, as we know that will be resulted in high power consumption and more heat dissipation, and the second one is by reducing the clock cycles. So we focused on the second technique, that is instead of focusing for a fixed frequency, by reducing the clock cycles we have increased the throughput. So here the clock cycles are entirely, that means directly proportional to the multiplication, that means multiplications. Therefore, the reduction in multiplications is also resulting in reduction in clock cycles. That is resulted in higher throughput. So like we have analyzed power consumption, area required, throughput required and all. So here we significantly gain the profit in power consumption as well as throughput. But when it comes to area, in comparison with the existing technique, our proposed techniques are taking slight more extra, because for forwarding the bits, we need to store certain pre-computed values in the memory. But nowadays, earlier days, there was a huge cost for buying the memory, but nowadays the memory is not a problem. So that's why we neglected that memory requirement. Instead, we focused on power and throughput only. So this is the comparison graph of throughput between the various algorithms and all. That means first two algorithms are existing. That means last two algorithms. In the graph, last two spikes are existing algorithms and first three spikes are proposed algorithms. Similarly, the number of multiplications required for each exponentiation we predicted here. Yeah, we have also calculated energy computation by using this formula, which is given by again Montgomery in his research paper in 1984. So based on his formula, we have computed this energy, which whatever the energy we computed by using his formula, and the energy by simulating the algorithms in FPGA, we got almost equal values. There was a slight difference in the digit format, that means like after the dot. So those will be negligible only. Yeah, now we are now our conference theme is public key infrastructure and its applications. So now where we can use these algorithms? Okay, really, if you are using a high length key like 512 bits and 1024 bits, which may not be applicable to the IoT devices, because IoT devices are memory constrained devices, but the servers, banking servers, or the data maintaining servers, where we need huge memory, there these techniques are directly applicable. And as per the requirement of algorithm, that means we are having a choice from bit forwarding 1 bit to bit forwarding k bit. So it's not meaning that for every key the bit forwarding k bit is always giving the efficient result. So it is not true. Sometimes bit forwarding 1 may give efficient result than the bit forwarding k bits. If the key is containing more number of consecutive ones, the two consecutive ones, then bit forwarding 1 algorithm is performing better than the bit forwarding k algorithms. Now NIST is also using the same technique, that means modular exponential techniques, for multi-party authentication. Also there also these bit forwarding techniques will be applicable. So is time is permitting, sir? Yeah. So now the higher throughput we can achieve with the help of bit forwarding techniques, and we can also achieve implementing the same techniques with the help of multi-core architectures. So here in multi-core architectures, there are two kind of multi-core architectures. One is homogeneous multi-core and another one is heterogeneous multi-core. In heterogeneous multi-core architectures, the cores are performing different operations. But in homogeneous architecture, the cores are performing same kind of operations. It is a kind of heterogeneous and homogeneous. We are using different RSA algorithms at different cores, because first one is based on one multiplication, called general MSM technique, and the second core is based on second multiplication called BFW1 and all. So the cores, the algorithms which are available at cores are different, but the purpose of core, that means purpose of that course are same. In both the ways, we are computing the RSA algorithm and all. So here, for managing this core, we have designed our own controller and scheduler by using a priority queue. So here the scheduler will check the availability of a core. Then whenever the request for a cryptography transformation is receiving, then the scheduler and controller will check the availability of free core. So whenever the free core is available, then that operation will be given to that core. And it is not only allotting the operation randomly, it is also allotting the operation in a load balancing way. For example, if we want to perform k number of multiplications, k number of operations, then this controller is assigning almost k by 2 number of multiplication in each core. In that, the load balancing factor is also satisfying. So here at different cores, we are using two different techniques, and each technique, the power consumption is different as well as throughput is different. Time requirement is also different. So though we are performing the same operation with the same key, but by core 1, the values are different from the core 2. So in this way also, not only by using the forwarding the bits, but also by using the multi-core architectures, we provided diffusion mechanism also. That means at two levels, two kind of extra operations we are providing, that called confusion and diffusion techniques under. Okay. This is the description of controller, and this is the priority queue which we used in the controller. And this is the state diagram of the controller. First, initialize the processor. Okay, whenever there is a cryptographic transformation is available, then the controller will check the availability of a free RSA core. If it is available, directly it is assigned to the core. You can see that arrow mark from ready to allocate RSA core. Then it will complete the task, and result will be written in BRAM. So if the core is not available, suppose we are having only two cores, but we received 3 operations at a time, 3 cryptographic transformations at a time. Then only with the help of 2 cores, you can perform two operations. So third core will be kept, that means third operation will be enqueued in the queue. Okay, this queue, if you are assigning the priorities to the task, then the highest, that means highest priority in the sense, the priority which is having lower number will be performed first. Otherwise, the same queue can be act as a first come first served based on that. Okay, then first initially, if the RSA core is not available, then the controller will enqueue the operation. Whenever the core is available, it will be dequeued from the queue and will be allocated to the RSA core. And here enqueue and dequeue is taking only 1 clock cycle. Okay, so this is the high level description of a hardware scheduler. I'm not going into full details. So this is a BRAM. Whenever you are using a hardware device, so in software, okay, the memory will be allocated dynamically. But when it comes to hardware implementations, we need to allocate a dedicated memory. So we here in FPGA, for allocating a memory, we are having a a block called BRAM. That size will be depends on our requirement only. So here request and responses will be stored. And which will not be available for any intruder. Even the designer cannot cannot take this space into his account and all, because everything will be stored in the memory, which will not be visible to anyone and all. This is not the future of our proposed technique. It is the future of hardware design only. Okay, so after implementing the same cryptography techniques with the help of multi-core architectures, the throughput is almost doubled. The power consumption is also like doubled, because though you are using 2 cores, at 2 cores you are performing the 2 operations, therefore the power consumption will be increased proportionally, but throughput is getting doubled. So we not only verified the algorithms with the help of 2 core architectures, we have also verified this algorithm up to 32 cores. So that means the proposed algorithm where we designed a BRAM is supporting up to 32 cores. So if we want to scale it up to 64, accordingly we need to increase the BRAM size also. Now already indirectly in the entire flow I have discussed about security analysis also. So these techniques are not vulnerable to the any side channel attack. And of course, these are also not vulnerable to the current existing post-quantum cryptography techniques and all. So the current existing post-quantum cryptographic techniques, what is that? Breaking the keys by using brute force, uh, by making use of the power of computation. As of now, there is no new technique to recover the key. So the only available technique, even in post-quantum cryptography, also brute force, that is trial and error technique. So you can increase the security just by increasing the key size. If you are increasing the key size, then for example, if your key size is 1024, then brute force needed 2 power 1024 trials. As of now, that is impossible to break it. At least 21 years, as per literature I am telling, to break that 1024 bit key by using brute force, at least 21 years time is needed. So with this, I am concluding my presentation. Thank you for giving me this opportunity.
Any questions?
Sorry.
Hello, your bit forwarding algorithm, how it compares with high radix Montgomery?
Sir, I am not bit forwarding algorithm.
How does it compare with high radix Montgomery algorithm? High radix means more number of bits to take at a time.
Sir, actually here two different operations are there, sir. High radix Montgomery multiplication is to evaluate the multiplication. Here bit forwarding technique is meant to evaluate the modular exponentiation. Even in bit forwarding technique also, we can adopt high radix Montgomery multiplication. Thank you.
Sir, please. Thank you so much, sir, for such a insightful session. I would now like to request Shri Anup Kumar Pandey from CDAC to felicitate sir with a memento. Sir, please.
Already completed, right?
No.
Thank you, sir.
Thank you so much, sir.